Hello guys, today what I want to do is I want to go over an example of gas collection over water. This is a fairly common way to capture gas when you do an experiment. And this is about as old as chemistry is. They realized the easiest that they had to know the volume of the gas to really describe the gas, and the easiest way to figure out the volume was to let that gas kind of bubble into a liquid filled container and see how much of the water got pushed out. So I'm going to talk a little bit about this method, and we're going to work an example to prepare you for a little bit of work that you guys are going to do on this stuff. So let me get my lamp on this. So the example I'm going to go over basically says that a sample of solid potassium chlorate, that's KClO3, is heated in a test tube as shown. So you would have like a Bunsen burner that was underneath this. And of course, a flame that's going to come up and heat up that material. And you're going to get a chemical reaction that occurs. It's the decomposition of KClO3. So this material would basically break down. And as you can see in the reaction up above here, that what you're going to have, your products from this, you're going to get KCl. Still be a little bit of solid that's left in the bottom of that test tube. But the other product you're going to get is you're going to get some O2. You're going to get some oxygen. And that oxygen is going to make its way through this tube and then down and into this container. Now, this container would have been completely filled with water to start with, much like you would do if you were in a swimming pool with a plastic tumbler or something and you fill it with water and then lifted it part way out. Water would be all the way up to the top. And so as the oxygen made its way down this tube, it would bubble through that water to the top of this container and fill this container up. Now, the thing is, if you do that, not all of the gas that's inside of here, and this is why we're doing it now, because this is a partial pressure situation, not all of the gas that's inside of here is going to be 100% O2. There's also going to be some water vapor that is in that container. So what we basically have to do in this case is, because we're really only interested in how much O2 came from that reaction, we're going to have to get rid of the water. Somehow we're going to have to figure out how to discount the pressure generated by the water. Okay? So that's what this question is really going to be all about. If you look at the question that's actually posed down below, it says the oxygen produced was collected by displacement of water at 22 degrees C and a total pressure of 754 torr. Okay. The volume of gas collected was 0.650 liters, and the vapor pressure of water at 22 degrees C is 21 torr. Calculate the partial pressure of the O2 gas collected and the mass of KClO3 in the sample that was decomposed. Okay, so I'm going to figure out, so the first thing we're going to do is we're going to determine the partial pressure, and we would usually just write pressure, O2. We want to figure out what the partial pressure of the O2 is. That was one of the questions that they asked us. Okay, to do this, I'm going to use Dalton's law of partial pressure, which basically would say that the total pressure, or P total, is going to equal the two partial pressures added together. So it would be the pressure of the O2, the partial pressure of O2 gas, plus the partial pressure of the H2O gas. So it's the combination of those two. And we know what the total pressure was. It was given to us. It said the total pressure was 754 torr. So I know that this is 754 torr. So if I want to figure out what the partial pressure of the O2 is, all I would have to do, this math is fairly simple, I would take the total pressure and subtract the pressure of the water to get the pressure of the O2. Okay, so once again, I know what the total is. It was 754 torr minus, in the question they gave me the partial pressure. These are known values. If you have a certain temperature, you're going to get a certain amount of water evaporating, and that's going to produce a certain vapor pressure. And that number at 22 C, which is the temperature we're at, is going to be 21 torr. So all I have to do to get my partial pressure of O2 is subtract 21 from 754. And if I do that, I get the partial pressure of O2 is going to equal 754 minus 21 is 733 torr. Okay. Now, before I can really use this for anything else, I will tell you in a minute, I'm going to do a little bit of stoichiometry, and I'm going to have to use PIV-NERT. Now, when I use PIV-NERT, remember that the units in the ideal gas constant, that's 0.082006 liter atmospheres per mole Kelvin. This pressure is going to have to be in atmospheres before I can use it. So I'm just going to go ahead and make that conversion right away. I want to go from torr to ATMs. And to make that conversion, time sign fraction bar, I want torr on the bottom. I want ATMs on the top. And then remember, I need to put numbers in here that are basically going to be equal pressure. So I would say that 1 ATM is equivalent to 760 torr. If I do that math, what I end up with 733 divided by 760, what I should end up with for pressure is 0.9645 ATMs. Okay, so that is the pressure of the O2, and the O2 alone. This doesn't include the water because we subtracted it out. This is the pressure in ATMs of just the O2 that was produced. Okay, so I now know what that pressure is. What else do I know about this O2? You know what I'm going to do is I'm going to rewrite the reaction here. So I've got 2K ClO3 yields KCl plus 3O2. And I know the pressure of the O2 was 0.9645 ATMs. I know the temperature of this O2. The temperature of that O2 is 22 degrees C. I'm going to go ahead and add 273 to that to convert it to Kelvin because I know I'm going to have to do it eventually. So if I add those, I get 295 Kelvin. And I also know the volume. The volume they gave me right off the bat, they said that volume here was 0.650 liters. Okay. So if you think about what I have here, I have pressure, I have temperature, I have volume. I have what I need to determine how many moles of that O2 gas that I have. Remember, what they're actually asking for is the mass of the KClO3. So I'm going to have question mark grams of that material. I already know the first question they asked, which was the pressure of the O2. So what I'm going to do is I'm going to use PIV-NERT and solve for N. I'm going to figure out how many moles of O2 that I have. Then that'll allow me to use the moles of O2 to convert to moles of KClO3. This is stoichiometry. So I'm going to solve this for N. And if I do that, that would give me PV over RT if I'm going to solve for N. So N is going to equal PV over RT. And again, I know what the pressure is. The pressure is 0.9645 ATM. Okay, times the volume, which is 0.650 liters. Okay, so those are the volume of the gas here, the pressure of the gas, of only the O2 gas, as we back the water out, divided by R, which we know is 0.08206 liter atmospheres per mole Kelvin. Okay, and the temperature, we already changed that to Kelvin. It's 295. Okay, so let's go ahead and figure out how many moles of O2 that we have in that space. If I multiply 0.9645 times 0.650, then divide by 0.08206 and 295, the number I got when I did that was 0.0259, okay, 0.0259 moles of O2. Okay. Now, could I have just used standard molar volume to go from moles to go from liters to moles? The answer to that question is no. We're not at STP, so I couldn't use 22.4 liters per mole. Okay, I couldn't use that because I'm not at STP. So we now know how many moles of O2 that we have. I'm going to start this final calculation, the actual stoichiometry here. I'm going to start with that. 0.0259 moles O2. Where do I want to end up with this? What's the question asking me for? Well, if you go back up here, I can see that the thing they're asking me for is the mass of the KClO3. So what I want to know from this calculation is grams KClO3. That's where I want to end up. I don't have the right substance. I know I need to convert it. Can I use mole ratio right away to convert from this substance to this one? The answer to that is yes, because we're already in moles. So I'm going to say the number of moles of O2 that I have. So I'll say moles O2. On the bottom, I'm going to say moles KClO3 on the top. And if you look at the balanced equation, I rewrote it here. The KClO3 had a 2 in front of it. The O2 had a 3 in front of it. So this is going to be 2 and 3. Okay. Unit-wise, those moles of O2 cancel. And right now I have moles KClO3. Now, it's the right substance, but I don't want it in moles. I want it in grams. So we need to use molar mass here. We're going to need to use molar mass where I have moles KClO3 on the bottom and grams of KClO3 on the top. Remember, the mole term here is always 1 when you're looking at molar mass. This potassium right here has a mass of 39.1. The chlorine is 35.5. And the oxygen is 16 apiece times 3. 16 times 3 should be 48. If I add all of those together, I get the molar mass of potassium chlorate, which when I did it came out to 122.6 grams per mole. We're almost to the end here. Our units will cancel. If you look at the unit I have right now, it's grams of potassium chlorate, just like I wanted. So we can go ahead and do the math. 0.0259 times 2 times 122.6 divided by 3. And when I did it, the answer that I got was 2.12 grams. So that's how much of that potassium chlorate must have been in that test tube in order to give me that quantity of O2. All right. So that's an example of these types of questions. Remember, the important thing here is I have to determine how much of the actual gas that I have, because it's basically in a mixture with water vapor here. And we need to back the water vapor out, since that water did not come from the actual reaction. That water came from the fact that it was sitting over the top of more water, and water is going to evaporate that space and increase the pressure that's in there. So we got to get rid of that pressure that the water created. Okay, so there's going to be a couple more questions that you guys are going to get here that deal with these kinds of problems. I think it was number 67 and 68, but I'll confirm it with you guys. So I'm going to leave you guys to that. You guys can work on the problems, and as we kind of make our way through this chapter on gases. All right, that's it, guys. I'll see you later, and don't forget to ask for help if you're stuck.